This follows faculty Inquirere. Inquirere means to inquire, it's Latin, and it's the term we use for evenings of speeches where people can present their academic research or other topics of interest. Later in the semester, we will have a student Inquirere evening, but tonight we have 3 new faculty who will be joining us to present what they've been writing about. This first presentation will be by Bill Noblock, who earned his BA in History from Northland College, his MA in American History from Northern Arizona University, and a PhD in 20th Century American History from Ohio University, where he also was a 2-year fellow of the Contemporary History Institute. He's the author of the book Nuclear Freeze in the Cold War, published by University of Massachusetts Press, UMass Press, and co-editor of the Rutledge History of World Peace since 1750. The work in this presentation appears in Making the Unseen Visible, Science and Contested Histories of Radiation Exposure, published by Oregon State University Press. Dr. Noblock.
Hi, thanks for being here on a day tonight. Hopefully, if the tech goes out, please let me know. So this talk is about Chernobyl. I'm a historian specifically of the 1980s, especially foreign policy, popular culture, and politics. And so a lot of my previous work had been done on nuclear weapons. This work is more done on Chernobyl. Many of you might have had a renewed interest in Chernobyl from the HBO series that came out a number of years ago, which is very well done. And that is not what sparked me, but I'm just writing the coattails of the topic. I was actually reading into this stuff before this came out, so I was very, very much interested in it. So just, if you're not a historian, meaning you make a living wage, if you're not a historian, you probably don't really know the historiography that well, or as well as I do, about 1980s in the Reagan era. So real quick, we're just going to cover some of the greatest hits of that historiography. Okay. The Reagan era starts in 81, yet it's the 79 nuclear reactor meltdown in Harrisburg, Pennsylvania, at the 3 Mile Island plant. That really sort of rekindles atomic anxiety in the United States. That's a much longer story. It's in my book. If you have trouble sleeping at night, I can show you what it is in the library. That's 79, then 86, Chernobyl, Pripyat, modern day Ukraine melts down. It's the largest nuclear reactor accident in world history. Okay. And in those 7 years, historians have done a lot of work, especially analyzing missile defense and strategy and foreign policy. Less so with nuclear power. That's what this talk is about. Okay. In his first term, Reagan was a very hardline rhetorical speaker against the Soviets, especially after their invasion of Afghanistan. And most people see that flipping around 1984. Some people call it a reversal. And that's the normal historiography, but almost none of it mentions the Chernobyl accident more than in a passing sort of mention or a footnote. There's like another thing that was kind of going wrong in the Soviet Union. So my argument is quite a bit different. Okay? So the normal argument is that Gorbachev and Reagan met, started to get along, started to cool superpower tensions, and then in the end the Cold War ends. No, not quite. There's a lot more to it than that. I'm a historian, which means more than anything I'm unoriginal, so I put my thesis right up front. And this is my argument. My argument is that 3 Mile Island and Chernobyl were both diplomatic cudgels that the Reagan administration had used, and the Soviets attempted to use in '79, to attack the other Cold War superpower. You start digging in the archives, you start reading some of this stuff, it becomes very enlightening. And just as a quick aside, and I'm watching my time, I got my time here, but just as a quick aside, a lot of these administration officials write books 20, 30 years after the fact, maybe just 10 years after the fact, and historians use those books. But if you read those books written 20 years after the fact versus the archives and the memoranda they wrote at the time, they're either lying or they're really misremembering what happened. And that's the fascinating part about diving into all this stuff. So let's just get started with the meltdowns. 3 Mile Island, 1979, Harrisburg, Pennsylvania. Here it is. Last political history conference I went to, this was inside of the airport. Felt fitting. Essentially, there was a reactor problem based on a gauge that probably didn't cost more than $1, which misread. The engineers didn't know how to respond to this. And I'll leave the particulars to any nuclear physicists in the room if we have any, but the particulars were this almost became a full-fledged meltdown, but it was able to be contained with some radioactive leaks into the nearby Susquehanna River, and this was a big news story, obviously, but became a bigger news story because an actor named Michael Douglas had produced a film called The China Syndrome, which eerily mimicked the events in Harrisburg and came out 2 weeks after the event. So, whoa, this all ties together and people are really starting to get interested in this stuff. And at the time, the United States had its only president who was a trained nuclear scientist, at least to some degree, Jimmy Carter. He worked on a nuclear submarine. So this is the thing, Carter is president, Reagan's not yet president, Reagan's running for president. This should be Carter's opportunity, and he totally blanches on this. He micromanages, which is sort of his want to do, and he doesn't give any real strong indication on how to respond to all this. Reagan characteristically has a very strong stance. And he's been honing this line because he's been running for president basically since 1968. By the time he leaves the California governorship, he's 100% for nuclear power, and he uses that as sort of his way to sort of promote clean energy, as he would call it. But this is all the rage for the Republican circles. After 3 Mile Island, Soviet publications such as Pravda and the TV station TASS started reporting on 3 Mile Island as the inherent weakness and the ideological weakness of capitalism. I have examples of that, but I have a time limit. But I wrote it, it's in a book, the book's in the library, I don't want to bore you with it all, but the attacks were coming. That this was what happens in a capitalist system, right? Don't worry, the United States would have a chance to respond. In Reagan's first 3 years, he had dismal superpower relations with the Soviet Union because 3 Soviet premiers died within 4 years. And Reagan even said, I'd like to do something, but they keep dying on me. But then, Gorbachev, who's very much a different, less of a military hardliner, more of a people person, a communist with a heart, if you will, comes into power, and he has 2 famous proclamations that some of you will remember vividly, and some of you probably have still heard of. One is perestroika, the other is glasnost. And these basically mean 2 things. One, perestroika is a restructuring of the Soviet economy to put more money towards food for people and less towards missiles. That's basically it. Glasnost is openness or more transparency in this perceived closed society. These are the proclamations. And those who study Reagan know that their first meeting to curb the nuclear arms race ended miserably. Reykjavik was a failure, it ended in a stalemate, there was no winner, and there was no arms negotiation that was met. Then by 1986, 2 things happened to change the course of superpower relations. The first is kind of sad. It's the Challenger explosion of 1986. Some of you probably remember this. This is embedded in some of our young minds. This was a super popular shuttle launch because of the inclusion of Christy McAuliffe, who was a high school teacher who was selected to be part of this, and tragically, it ended in failure. This was one of Reagan's probably 2 best-known, maybe 3 best-known speeches. He co-wrote it with Peggy Noonan, the speechwriter. And it has a very famous line that the great communicator had about how when these people died, they escaped the surly bounds of earth to touch the face of God. And this became one of Reagan's lines. And it totally overshadowed a later line in the speech that historians don't talk about too much, which is this line. And this is the thing you have to remember. Like, for all the talk historians have about Reagan the reformer and Reagan, he could not stop poking the bear. He could not stop. He loved it. He loved to tout American superiority and the inferiority of the Soviet Union. So even in the wake of this crash and this tragedy, he said, this is how we do things in America. Even our mistakes are out in the open. We do things publicly, we like freedom. He's attacking the Soviet Union based on this. A better attack point is after the Chernobyl disaster. Who here's seen the HBO? It's pretty good. And it's fairly accurate. There's some made-up characters, but it's pretty good. It gets a lot of the major points right. For example, Gorbachev did not publicly acknowledge the scope of the meltdown for 18 days. This is after his proclamation of glasnost and openness and transparency. The thing about radioactivity is it does not respect your national borders. And so when Finnish scientists picked up on, was it Finnish or Swedish, Bill, if you remember? I think it was Finnish scientists first pick up on the radioactivity. Yeah? They don't think it's a bomb. They think it's a nuclear plant, and this is where the Soviets start to crack with glasnost. Okay? Those of you who've seen the design or have seen Chernobyl know the design. The big flaw in the design was something that pundits in America pointed out after 3 Mile Island in 1979. They said, the reason we didn't have a total meltdown is because we have safer nuclear plants than the Soviets. We have more safety precautions in place, specifically the domes that we have capping over these things, which the Soviets did not. This is the basic design of their nuclear reactor. This is the design that exploded at Chernobyl, resulting in the largest nuclear meltdown in history. It had no safety cap over it that was sufficient to contain it. By comparison, you should know that the 2 million pound cap they had blew completely off. So it was not close to sufficient or necessary to do this. Yeah, go ahead. Jeez.
The Soviet design would be the same?
No, the American design and the Soviet design were very different. The notable difference has to do with the cap over the top, and I'm not a nuclear physicist, but the experts I read in the newspapers and the articles were very clear in pointing this out. And once we get to Chernobyl, they go back into the newspapers like the Wall Street Journal, the New York Times, the Washington Post, and they put out ads saying, Chernobyl can't happen here, our technology is better. Our technology is different. Our ideology is better, is also kind of what they're saying. The Soviets say this isn't that big of a deal, only 2 people have died. Reagan had CIA information that probably more than 2,000 to 3,000 people in the first couple days had died. So he knows that they're lying in the face of glasnost. And then he gets CIA estimates that show they've been hiding these things for a long time. There are a number of nuclear power reactor accidents in the Soviet Union that the Soviets have tamped down publicly. Now is the time to expose them for being liars. Okay? And here's the most interesting turn of events for me in studying this. This coincided with a G7 summit. Now it's called the G8 because there's another nine like the other nations. G7 summit. This was in Tokyo, Japan. Reagan gets word primarily from the head of the National Security Council, Jack Matlock. Now Matlock in his memoir says, we didn't use Chernobyl as a diplomatic cudgel. We used Chernobyl, it was a humanitarian effort. Lies. I mean, the memoranda are clear. We have to attack. This is an opportunity. We can expose them for being bad people, et cetera, et cetera. What I love about this is that Reagan is known as sort of the deregulator in American conservatism. He initiates not just a national, but an international regulatory rule to punish the Soviets. This is his idea. He promotes it at the G7, and in time, the International Atomic Energy Association will adopt it as a rule. Okay, so here's just a quote about him saying the Soviets totally blanched on this. It was a total problem, and the whole world community has a right to regulation. This comes in the form of the Convention on Early Notification of a Nuclear Accident, or CENA referendum. The great deregulator has created an international regulation, all to punish the Soviets, and Gorbachev is ticked. After 18 days, he finally goes on task to give an announcement. He doesn't look good. He's clearly haggard. He clearly has to come and admit that his earlier proclamations about a new Soviet Union are not the case. He's kept this under wrap for 18 days. And was it his fault? Could be. Perestroika, sort of this restructuring, meant we need more energy for commercial power. And the KGB said, perhaps this is not safe with the type of reactors we have. Doesn't matter. Has to be done. So it's after the call for perestroika that glasnost, or that Chernobyl actually happens. This language is pretty revealing. Certain NATO countries are rumbling, saying bad things about us. So the diplomatic rhetoric is on, okay, between Reagan and Gorbachev. And this is in the face of these peaceful meetings they're having that are making the news, but they're still throwing jabs at each other. The recently declassified memoranda are probably the best because they do show, and this is what I love about the Freedom of Information Act, they do show that some of these later memoirs are basically falsehoods, that people were saying use Chernobyl to attack and discredit the Soviet Union. Okay? So from Challenger through Chernobyl and on into the later 1980s, this remains a sticking point in rhetoric between the superpowers. Okay? This is part of the internal memoranda saying that we have certainty that we can refute the Soviet accident and feel safe on our own side because our technology is different. And in fact, we should promote to the American public that our technology is better because we are Americans, and that is exactly what they do. These full-page ads appear twice, 2 different Sunday insets of New York Times, Washington Post, Wall Street Journal, etc., explaining that 3 Mile Island and Chernobyl were 2 very different things. And ergo, it is the United States who has superior nuclear power. O'Gorby did not like that. But it worked. And if you were to look into Reagan's diary near the end of his presidency in 1988, and I forget the exact date, September 1988, there was a nuclear reactor accident for a Soviet sub in the Caribbean. So a Soviet sub in our hemisphere has a nuclear reactor problem. Gorbachev informs Reagan the same day. And Reagan writes in his diary that night, Chernobyl must have had an effect. We got to him, right? So now that transparency that he was lying about has to happen because the international community is monitoring the Soviets and everything nuclear having to do with them. So I'm summarizing it because I'm a historian and that's what we do. They used Chernobyl to attack the Soviet Union for being ideologically and technologically inferior to the United States. The Sina resolution of October 86 definitely had paid dividends for Reagan when Gorbachev acknowledged the nuclear sub-problem. This was another way to have an ideological war versus a war based on, say, human rights or technological superiority. And they stung a lot more after the huge promotion of glasnost and perestroika by Gorbachev. So, yeah, it's like a 30-page chapter, and I just want to whittle it down and not bore you too much, but I have some more images. I do love that in some of these cases, when you look at the memoranda, like the speechwriters had crossed out Reagan's line, we don't hide our failures, we do everything in the public. He put it back in. He could not miss a chance to attack Gorbachev, which I love. And then, if any of this is remotely interesting to any of you, these are just some books I might recommend on the subject, which are probably better than my book. And then a picture of Chernobyl if you have any questions today. The wolves are loving it. They're running around having a great time. Thanks. Minutes, right? That's good?
Yeah, perfect. Now we have time for some questions. Can I pop one in quickly? You said
Sure.
the wolves are enjoying this, yeah. They're getting medical problems because of...
Some are, but they see, it's an interesting thing, right? So wilderness, by definition, is an area untrammeled by man. That's a classic definition of wilderness. So by that definition, radioactive places are pure wilderness because man cannot trammel there. And you've seen this rise in fox populations and wolf populations, bird populations. And they seem to be doing okay, but I don't think that old habits. I don't think Russian scientists are running in there testing them every day. I don't know. But there's stories on the news left and right about this is amazing what's happening in Chernobyl. And you can still go visit. I wouldn't recommend it, but you can. It's open. You can stay for like 2 hours or something, but I wouldn't do it. There are better vacation spots.
In your research, what was the biggest surprise?
Seeing that Jack Matlock had lied in his memoir, or forgotten, but it's Matlock, it's fine. That he had lied, and also seeing that Reagan was reinserting things his advisors were taking out because he just couldn't let it go. Like he still had to really tout American superiority over others. But there's tons of quotes. I still won't put people to sleep, but there's tons of quotes from NSC staff about like, this is the time, we got to attack, blah, blah, blah. But I think the president and Gorbachev's quotes are a little more revealing than the behind the scenes ones. So it's fun. It's fun stuff.
The live stream can have you.
Yeah, no, yeah. I know, I can't. Yeah.
I know this question is adjacent, but as a historian that studied this, do you have a point of view about more countries investing more in nuclear energy now?
Energy. I don't blame them, right? Because at some point you want energy security from, say, oil and fossil fuels. It's the devil's bargain a lot of countries make, because what are you going to do with the waste? Because the waste is going to be bad for 10,000 years. The thought exercise I do with my students about the waste is, you have to make a sign to tell people not to come here because of nuclear waste work. So just say don't trespass. Say English won't be around. There will be no English language. Just like you don't speak Latin. You can't do that. These problems are long reaching. But they're still seeking power because why not pay yourself, right? Philip, I see your...
Yeah, I'm sorry.
No, don't be sorry.
Years of, that's the big thing, they've been researching to get rid of waste. And there are huge steps forward into that, and I think Japan is starting to build one. I think this is global news. And it's using a method that actually takes the waste and they reset it and put it back into their reactor.
Sure.
So
That's...
it completely getting rid of it. And
Okay.
Japan's like...
So you just whittle down the half-lives to like nothing?
No, it's more that you take your waste and then you clean it and you put it back in the reactor. So your fuel source goes back in.
Yeah.
Right? So half-lives don't mean anything because you're bringing it back.
Yeah, okay. Oh, I didn't know.
There's like 10, 20 different styles of nuclear reactors now because of this move to not have nuclear waste.
Okay. I know that in the American West, it's been very antiquated. They're just trying to find holes in the ground to bury the stuff away from it and things like that. So it doesn't surprise me that Japan, they use so much nuclear power, they would be innovators on this. That makes sense. Give me more questions. Yeah.
I just wanted to know kind of what the perception was from the Soviet Union's, the general population. Like, what was the propaganda looking like on that front? Like, do we have these full-page ads in major newspapers? How does Gorbachev deal with that?
So the two official arms of Soviet state propaganda, TV was TASS and Pravda was the print, and they, for 18 days, they just kept their mouth shut about it, or they really downplayed it. Some said like 3 people hurt, later like 200 people injured. It's probably 10,000. So they downplayed it. Now, what you're kind of asking me is, did Soviet citizens believe that? I doubt it. I doubt it. At that point, I doubt it. It's sort of like you accept the lie and you sort of move on, but I can't speak for that culture too much. That's a great question. It's awesome. Yeah?
How did they keep the word from getting out from the people who were evacuated?
Right? They were concentrated into a nearby, I think just outside Pripyat, they were concentrated and told not to leave. So the military comes in, but the citizens are put on lockdown, so they can't leave. In part because they're contaminated. Just in fact, you could hurt other people and stuff. But hard to keep the news quiet. Like you couldn't, this reactor leak was epic, biblically epic, very bad. Another fun day in history. This is really light and fluffy compared to the nuclear war stuff I do. So is that it?
So what was the inflection point for Reagan and Gorbachev, kind of their relationship, kind of moving closer together?
Yeah. They got along at Reykjavik okay. They both wanted a reduction of nuclear weapons, and if they stuck to that point, they found pragmatic ways to. That's what ended up with the INF Treaty of 1987, the Intermediate Nuclear Forces Treaty. The medium-range missiles in Europe were the biggest threat because from launch to detonation is like 7 minutes, and launch to detection is like 6 minutes. So it was very dangerous in Europe, especially during the 1980s. They would annoy each other. Reagan really annoyed Gorbachev. He kept talking about little green men from outer space, that if they would come here, that the superpower Cold War would end because we'd have a common enemy. And he'd be like, he's going on about the aliens again. But Reagan loved that. So I think they ended up liking each other and appreciating each other, but if it came to ideological debates, it was boom, boom, boom. But when they could agree on one thing, the nuclear, to reduce nuclear weapons, then they found ways to get along. Okay, cool, thanks.
Thank you. We'll now take a 5 or 10 minute break to set up for the next speech. There's plenty of food waiting for you over here. Try some things.
I think we're just gonna stick with solar. The sun is pretty.
Wind is good, wind is good.
Talk about nuclear again, 3% rise in electric needs for data centers in the Midwest, in water.
I was super shocked today when I told them about how they're taking over groundwater and the rural data world about denial easily. They were like, what? And they're all like, yeah, everything you do is Google search. And they were just, how do we have about this?
Don't get around by metric levels.
Oh, yeah.
That will disappear.
We're talking about the animals. I feel like recently I saw the first dogs from the area were allowed to be about outside.
Wow.
There are organizations which take our animals there because they all left, right? And so they take salt, so they stay in control and we can't reach the ones so that. But I do like recently, I read an article about one was allowed to be outside of the.
What if you checked it for application?
Oh, of course they did. I'll have to try and find it and make those.
Huh?
He made this.
You doing all right?
Oh, yeah.
So, it's been helpful in Marquette for a while.
How is it Chernobyl,
It's like 17 in Marquette.
the current?
Yeah.
I want to know.
Was it, at the beginning, there was talk about another Chernobyl targeting nuclear plant?
Yeah, I remember that.
Because the Soviets raided it, sorry. The Russians raided it. And one of the first things they did was take these open nuclear units. And everyone was like, they're going to control the power. It's a threat. They could have a meltdown. They could. Yeah, so, but that died down. So I don't really know lately. I haven't heard much about nuclear power in Ukraine lately. But the outset of the war was a big deal.
It doesn't seem to be, I mean, all the stories now seem to be on Ukraine attacking oil refineries, power.
Of course.
Yeah, so when getting this ends, how did they tackle like the rehabilitation of Chernobyl or the power?
Shit, that's a good question. I don't know the answer. You can't, well, what, just be on the It's done. I mean, the town is dead. We're not getting back. So, but what did they do about maybe making other reactors? I don't know, I should look into it. This was really written from a foreign policy point of view.
Oh, but yeah.
So I don't really know about the medical or something.
Aren't the devs of the Scotland series was that Chernobyl Ukraine?
That's what I'm.
Should they do excursions?
Well, it is in
So it's like the kids are always
Nice to meet you. Okay. Very nice to meet you. Okay. Wait. Yeah. Sorry, set the side. I set the side.
Having fun. Yeah.
And then everyone smells. Like,
Where are you?
no.
Oh my. Okay.
The thing is, remember, it's not market-based. It's market-based. We could have an argument about that, but it's not. But because it's not market-based, it's Gorbachev is the power. We need more power from Eastern Europe. So it wasn't that short to push this thing. So, yeah, I feel like, Jesus, why'd you do this?
I don't think so. Was it a process? We don't have that physical.
Yeah, we're in Eastern Europe. Yeah, that was the dictate. As part of perestroika, you just, I have I guess it was the NSC declassified. That's why we did this.
Yeah.
I think we're trying to announce our presence. Sure. It was mostly
Probably 48 hours after.
Yeah, the original person.
It was the NSC that was the first to tell me, and all those, the communiques would come in, it's like, it's April 29th or something.
Okay, our second speech of the night moves from history to psychometry. Dr. Nikki Klaus is an assistant professor of psychology at Waldorf University and a former NIH IRACDA scholar. Her research examines how stress and biological sex shape dopamine and reward in humans and rodents, using techniques like a high-speed chronoamperometry, fiber photometry, and optogenetics to address real-world issues in addiction, including alcohol-stimulant interactions. As a passionate educator and mentor, she strives to use her background to create inclusive, active learning classrooms and mentorship pipelines that help Waldorf undergrads grow as scholars, professionals, and community-minded citizens.
Thank you for coming out and listening to me talk about this research. I'd like to add that I am also an amateur race car driver and part-time tattoo artist. So, before I came to Waldorf, pretty much all of my work centered around this central question here, which is how can secondary uptake 2 neurotransmitter transporters influence neurophysiological processes underlying substance abuse and stress-related psychopathology. So I realize that that's a lot of jargon, but don't be scared. I'm going to actually introduce all of those terms to you throughout this talk today. So before I do that, I want to mention that during my time exploring this central question, I found a role for these uptake 2 transporters in a bunch of different things. And so I found a role for them in the rewarding effects of amphetamine, where I also found some really interesting sex differences. I found a role for them in fear memory circuitry, neurocircuitry. And I also found a role for them as a site of action for alcohol, which I'm going to be focusing on today. And so, I don't know how many of you guys know anything about this, but people who drink apparently really typically love to take cocaine with their alcohol. I did not know that this was such a big thing until I started working in the pharmacology realm. And so, we could study many substances, which I have, but this particular pairing just keeps coming up in the real world, and it's especially dangerous. So I'll show you why these two together deserve our attention. And so first, alcohol use disorder is So this means that alcohol is often already in the room when other drugs show up, right? And so when people use cocaine, they're frequently using it on top of alcohol. Not only that, the fact that alcohol use disorder is so common, but 33% of people with alcohol use disorder report also using cocaine. That's a huge percentage of people, right? And so this makes cocaine and alcohol an incredibly common drug combination. And so hospitalization and relapse rates, they're really, really high for individuals who use this combination of alcohol and cocaine. And so with that, that really makes it also one of the most dangerous drug pairings out there. Making it even more dangerous is the fact that there are no effective, approved medications for overdose on or addiction to this drug combination of alcohol and cocaine. Of course, counseling and support, they're very important, they're huge, they matter a lot, but our pharmacology toolbox here is really thin. So this pairing, being so common and dangerous and undertreated, right? It's exactly where understanding the mechanism can pay off. And so if we can find sort of the hidden levers, right? Like what I'm going to be referring to as the backup drain, and you'll hear about that next, we can really design smarter ways to prevent harm and help people recover. Okay, so transporters. I'm sure there's a bunch of neuroscientists in the room, right? So I'll talk about transporters real quick. They are essentially these proteins that span the cellular membrane of neurons, brain cells, right? So you can think of these proteins as sort of the brain's cleanup crew, all right? They decide how long these feel-good signals stick around. So their big job is to carry neurotransmitters across that cellular membrane and direct them to specific intracellular locations. And so they're sort of like vacuums or drains, which I'm going to be talking about. I'm referring to them a lot here. And by sucking up extra neurotransmitter back up into the cell for vesicular repackaging, and by cleaning up this excess neurotransmitter, they are effectively stopping or slowing the impact that neurotransmitter can have on nearby cell bodies. And so these transporters are a really big deal when we think about stress-related psychopathology and addiction. The simple part here is that there are two, what I'm referring to as main drains, okay? And so those are these well-known, famous drains, which are uptake 1 transporters. And then we have these quieter, sort of backup drains that we refer to as uptake 2 transporters. And so a lot of research and most textbooks really stop at this big drain category, right? So even if you're not a neuroscientist, you probably have heard, at least in some capacity, of like the dopamine transporter or the norepinephrine transporter or the serotonin transporter, right? So these transporters are really the first line of defense. They have this really high affinity for their named neurotransmitters, but they have a lower capacity to actually transport them, surprisingly. And so what I mean by that is that, for example, dopamine, right? The dopamine neurotransmitter, it's going to be primarily drawn to the dopamine transporter, first and foremost. But if there is like a lot of dopamine activity, then dopamine can sort of clog that dopamine transporter. And so it's going to be helpful, right, if there is another spot for dopamine to go. And so my previous work really shone a light on these lesser known backup drains, right? These uptake 2 transporters. And so these include organic cation transporter 3, or OCT3, and its teammate, plasma membrane monoamine transporter, or PMAT. I'm going to be talking pretty much exclusively about OCT3 here, but PMAT also does play a role in a lot of other things. But small changes in these sort of backup drains can really tilt the whole system. And so these transporters differ from those uptake 1 transporters, right? Because those uptake 1 main drain transporters, because these uptake 2 ones, they lack that affinity that I talked about, right? And so they lack the affinity, but they have a much higher capacity to actually transport. And so, as an example, OCT3, it is not dopamine's first choice, all right? It's not drawn to it like it is the dopamine transporter. But in the case where that dopamine transporter is clogged or oversaturated, then OCT3 can really pick up the slack and do some serious cleanup work. Okay, so on this slide, I'm showing you the same thing in 2 different ways, all right? So I'm showing you a sink on the left that I hand drew, so I hope it kind of clarifies understanding. And then I'm showing a synapse, which is this tiny gap between brain cells, okay? And I'm showing that on the right for like a biological comparison. And so, under normal, sober conditions, we think of dopamine like water from a slow faucet, okay? And so a little bit is always dripping to keep motivation and learning humming along, right? And so the brain has essentially 2 of these drains to keep the level steady. So we have the main drain, right? These are these blue dopamine transporter pumps that quickly pull dopamine back inside the cell. And then we also have these red backup drains, OCT3, for example, which are these high-capacity transporters that help clear overflow. And so cocaine and alcohol, they are both known to increase extracellular levels of monoamines like dopamine, which is what I'm focusing on today, dopamine. And so it's well known how cocaine does this. It's not a secret. It doesn't make more dopamine at the faucet. It instead parks on the transporter and it blocks it, right? And so it's like jamming gum in a vacuum or clogging a drain, right? With the main cleanup crew, those uptake 1 transporters, when them shut down, dopamine builds up outside of the cell. And the signal then gets stronger and lasts longer, okay? So we look at this sink cartoon that I drew here, and the faucet is just dripping, but the bowl keeps filling up, right? Because the main drain is plugged. So it's the same idea here. So not more water in, just less water out, okay? So that's cocaine's portrait here. But OCT3 is still active and available, so it begins picking up the slack here. So even though alcohol, we also know that it slows the clearance or that cleanup rate of dopamine, it doesn't have anything to do with the dopamine transporter, okay? Or that blue drain. And we also already know that when cocaine and alcohol are taken together, alcohol amplifies the spike in dopamine that we see with cocaine alone, right? That's why people take them together. The high is stronger. So the question is, how is alcohol doing this if it's not doing it via the dopamine transporter? And so what we proposed is that alcohol is actually slowing the clearance, or I guess the drainage, using my terminology here, of dopamine by clogging that OCT3 backup drain. And so the idea here is that if alcohol partially jams that OCT3 backup drain while cocaine is jamming that primary dopamine transporter drain, then dopamine hangs around longer, right? And backup gets larger. So because dopamine lingers, cocaine's rewarding effects should get a boost, right? But only when alcohol can hit OCT3. So if OCT3 is the route that alcohol uses, then blocking or removing OCT3 should erase that alcohol boost. And so the take home here overall is that we already know that cocaine jams that make dopamine reuptake vacuum or drain, the dopamine transporter, right? That is something that we know, and we expect that alcohol clogs the OCT3 backup drain, which is what we're testing and what I'm going to show you. And alcohol and cocaine, when you take them together, they create this dopamine traffic jam, right? So more dopamine outside of neurons, more rewarding effects. And if OCT3 is the key here, then targeting OCT3 should control that synergy, right? So I'll show you what we did and some of the evidence that we have here. So this is how we measured dopamine in a living brain in real time. So on the left here, we have our setup, all right? And so we use this tiny recording sensor that we actually hand make. It's a carbon fiber electrode, and we lower that into, in this case, the striatum of an anesthetized mouse. And the striatum here is an important area of the brain for the reinforcing effects of psychostimulant drugs, all right? And so right next to it, you can see like there's the carbon fiber electrode, and then the other thing that's right next to it, that is a micropipette, which we also handmade. And that lets us give either a brief puff of dopamine or a test solution, okay? And you can think of it as kind of like a dopamine ping, all right? And so then what we do is we send this small, safe voltage pattern to the sensor. It's sort of like turning a microphone on and off really, really fast. And so when dopamine touches the sensor, it creates a tiny current. And so that current is highly reproducible, all right? So we can convert that, which we do, to a concentration. And each peak that you see on the trace here is how high the dopamine went, okay? And so two things matter on each peak. Peak amplitude, and so that's going to be how big the signal gets, all right? How much dopamine is out there. And then also something we call T80. And that's the time it takes for the signal to fall back down by about 80% from the peak. And so I call this our cleanup time. So a short T80, we have fast clearance, all right? Long T80, dopamine is hanging around. So because we can repeat this many times in the same spot, we get this stable back-to-back trace. And so that means we can compare conditions. And so baseline versus alcohol, cocaine, or genetic changes like removing OCT3, which is something that we did and I'll show you. So if a drug blocks cleanup, the peak might last longer and that T80 increases. And if it speeds clearance, then T80 is going to shrink. So chronoamperometry is basically like a stopwatch for dopamine in a living brain. It's letting us test in real time whether alcohol, cocaine, or OCT3 are changing how quickly dopamine is cleared. All right, so we did chronoamperometry in what we call wild-type animals, and these are just animals that have natural, normal expression of OCT3 in the brain. And we also did it in animals that had OCT3 genetically knocked out of the brain. So they don't have OCT3, so we know that any effect that we see in those animals, it's not going to be due to OCT3, right? So what we have here, what you're going to see here, is on the y-axis, you're going to see those T80 time course rate changes that I was talking about in these wild-type and knockout animals. Anything over 100% there is going to indicate an increase in dopamine clearance time. And so that means higher numbers mean that dopamine is sticking around longer. And so on the x-axis is the condition that it was measured in. So we measured dopamine after injections of either saline, alcohol, cocaine, or both together. All right, so as expected, saline administration does not impact dopamine activity, right? It's saline, that makes sense. It sits at that 100 mark, meaning that there is no increase or decrease in clearance rate in either wild type or knockout animals. But you can see here that after the administration of alcohol, we see this increase in dopamine clearance time in our wild type animals, meaning that it's taking dopamine longer to clear out when alcohol is on board. But that doesn't happen in our animals that don't have OCT3, which is a good indication that OCT3 is important here. Okay, and not surprisingly, cocaine also significantly inhibits the clearance of dopamine. And this happens in both our wild type and our knockout animals because both of these animals still have that dopamine transporter, right? That main drain. And so that's what cocaine acts on. And so again, that's not surprising because of all of the previous work that's shown this, but it's important that we do this and that we get the same thing that everyone else has got, right? Replication. All right, so you can see here that in our wild type animals, administering cocaine and alcohol together produces a significant increase in dopamine clearance time over and beyond either drug alone, right? We don't see this in our knockout animals because they have the dopamine transporter, right? They still have that. They don't have OCT3. So we only see the cocaine-induced increase that would be expected here, right? So altogether, this is giving us more evidence that alcohol is acting at OCT3 to inhibit dopamine clearance, which supports our hypothesis. All right, so this is all really exciting, but how do these animals behave, right? Is there any behavioral indication that this drug combination is more reinforcing than either of them alone, right? And so to answer this, we used something called condition-placed preference, or CPP, which is a procedure where the animal learns to associate a particular context with a particular substance. And we measure the animal's preference for each context with the idea being that the animal's going to spend more time or prefer a context that is associated with a pleasurable stimulus and avoid a context that is associated with an aversive stimulus. And so this process begins on day one, where we're habituating or sort of like getting used to the chamber and what we call intraperitoneal injections. These are injections into the stomach. So we're administering saline to all the mice via two separate intraperitoneal or IP injections. So immediately following the second injection, then we put them into this chamber. On day one, it's a solid floor inside the chamber. So days 2 through 9, these are our conditioning days. So during this time, mice are going to be injected with either saline only, saline and cocaine, saline and alcohol, or cocaine and alcohol, depending on whatever group they're randomly assigned to, right? So after injection, they're immediately placed in that CPP chamber on either a grid floor or a line floor. They have different textures. And these drug floor pairings are alternated every other day to facilitate associative learning. So finally, on day 10, we have our preference test day. And this is where we're administering 2 saline injections to mice, and we place them into the CPP chamber on a floor that is actually half grid and half line. And so we have a software program that uses these infrared beams that calculate how much time the animal is spending on either the line floor or the grid floor, right? And we quantify preference then by taking the time that they spend on the drug-paired floor and subtracting it from the time that they spend on the saline-paired floor. And so the average of that is what's plotted on the y-axis here. So looking at our wild-type animals, we can see that cocaine administration by itself doesn't produce significant CPP in males, as we use a lower dose of cocaine here. Now it does in females, okay, and that's not surprising. It is really well documented, and I found it over and over again in this research, that females are remarkably more sensitive to psychostimulants than males. So that did not come as a shock to us at all. Likewise, the administration of alcohol alone does not produce any sort of significant place preference in either males or females. But when we administer alcohol and cocaine together, we do see this significant increase in preference in the drug-paired floor compared to when either drug is administered by itself. And we see this in both males and in females. But this is what I think is a cool thing. We don't see any enhancement of place preference in animals that don't have OCT3. And so, again, this is really suggesting that alcohol is acting at OCT3 to enhance those reinforcing effects at cocaine, right? It seems to be necessary to have those enhancements. All right, so, how am I doing on time? Okay, all right.
You started a little bit.
Okay, good. I wasn't sure if I had time to talk about this, but I wanted to because every time I talk about it with my undergrads, they kind of giggle, and honestly, doing these experiments made me giggle a little bit too. So, we also were curious as to whether animals lacking OCT3 would be more sensitive to the hypnotic effects of alcohol, right? So that's sort of the relaxing and kind of sleepy effects that you get from alcohol. Because greater sensitivity to that particular effect of alcohol is associated with a higher incidence of alcohol use disorder. And we can actually measure this in rodents by assessing their loss and regain of this righting reflex in response to alcohol administration. So rodents have something called a righting reflex where if you put them like on their back, they have a reflexive need to get back on all fours on their walking surface, right? And so what we do is, first step is to get them really drunk, right? So we inject them with a lot of alcohol. So this was 3.2 grams per kilogram of alcohol. And then we just lay them on their back, right, in the supine position, like that. And then we measure how much time it takes for them to regain an upright position where all four of their paws are on their walking surface. And so the amount of time that they spend sort of struggling or sleeping in that supine position is what we use as the loss of righting reflex duration. So in these experiments, we not only used OCT3 knockout and their wild-type counterparts, but we also used serotonin transporter knockouts and their wild-type counterparts, because our lab had previously found that OCT3 is actually upregulated in those animals that are lacking serotonin transporter. So in other words, the animals who don't have serotonin transporters, they seem to grow more OCT3 to compensate, which is really interesting. And we took advantage of that. And so we have the duration of the animal's loss of righting reflex plotted on the y-axis as a percentage of their wild-type counterparts. And then you can see the genotypes tested on the x-axis. And we see that those animals that were lacking OCT3, they're significantly less sensitive to the hypnotic effects of alcohol. Alternatively, those serotonin transporter knockout mice who we found, again, to have the extra OCT3, they were significantly more sensitive to those hypnotic effects of alcohol than their wild-type counterparts were, which is really cool. So these experiments also suggest that these hypnotic effects of alcohol depend on how much OCT3 is expressed. All right, so based on these data that I've shown you today, it may be possible to pharmacologically prevent alcohol's actions at OCT3 and enhance OCT3 transporter function is sort of like a therapeutic approach, right? Of course, a lot of work would have to be done, right? This is just work with mice. But this approach really it has the potential to counter the OCT3 inhibiting effects of alcohol on that dopamine uptake and limit the increase in dopamine induced by cocaine. So that could possibly be an avenue to treat overdose and addiction to that particular drug combination of alcohol and cocaine. And just because none of this is ever done with just one person, I want to recognize everyone that helped with this work. My colleagues at the Medical University of Vienna, as well as my mentors and colleagues in the Dawes Lab at UT Health San Antonio. That is me and my co-author in Portugal. He's an introducing them to all kinds of crazy European foods. And that's what I have.
I think we have time for just a few questions.
I have a question, hopefully it makes sense. You talked about the sort of hypnotic effects of alcohol on mice who do not have serotonin reuptake.
Yes.
Word.
Yes.
Is that why in people who are prescribed, possibly is that way in people who are prescribed SSRIs, they're told to drink less alcohol because of the correlation? Because you said that those who were lacking the serotonin transmitters often had more OCT.
Yes. So yes. So if they, in the mice that we knock that transporter out completely, OCT3 is upregulated, so more of it grows on the cell, right? So actually, yes, possibly, because serotonin, or SSRIs are blocking the serotonin transporter, so that could prompt more OCT3. I don't know. I don't think anyone's looked into that, but that is a really good question, and I think that it's a possibility, yeah.
Because I think they say that one of the symptoms of taking an SSRI is that alcohol will affect you more in terms of
It does.
dizziness and the spins, et cetera, et cetera. So
Yes, you are definitely more, sensitive to those effects of alcohol, for sure. And there are other reasons for that, but I am definitely curious as to whether OCT3 might play a role there too. That's a good question. Yeah.
Given that alcohol and cocaine are acting on two different chemicals, would you expect their combined effects to be additive or synergistic? And what actually was it?
It was additive, actually. So, yeah, if cocaine is blocking that dopamine transporter, and if all of this is correct, which it looks like we've done a ton of experiments, and OCT3 is blocking, alcohol is blocking OCT3, then that would be sort of an additive effect, right? So cocaine and alcohol together, they're blocking both those mechanisms. That's not like an increase in release, but it is completely blocking any sort of reuptake with both of those in place, right? So that would be an additive effect. Yeah. Yes.
So what do you see as next steps for you in this research?
That's a really good question. With this in particular, I'm sort of in more background role. Now that I've moved away, I'm consulting and helping with writing papers up right now. I am still trying to figure out avenues to stay involved. So that's a really good question. Yeah.
I have a really stupid question. How do you get cocaine so high?
Yeah. I can answer both of those.
Try this at home.
You do actually have to order cocaine directly from the FDA, right? And it comes in a powder form that we make into a liquid form, and we inject it into the mouse that way. But yes, intraperitoneal injections in this case. Yeah. Yeah.
Did you notice any difference in how the mice reacted to each other?
Oh my gosh, yes.
Okay.
Yeah, that's a whole other thing that I always wanted to look into and never got a chance to, but maybe it was less with the cocaine as it was with the meth. I think this happened more with meth, because I also did a lot of meth. But after, yeah, no, I did not. When I injected the mice or rats, whatever I was working with that particular psychostimulant, they seem to be, the males seem to be more aggressive with each other, and the females seem to be more sexually aggressive with each other, which I thought was really interesting. And I never really got a chance to look into it more, and I know that that's a common behavioral thing, but as far as like whether OCT3 would play a role with that, I'm not really sure, but it would be interesting to look at. Yeah. Yeah.
So obviously alcohol and cocaine are often together because of partying and they're party drugs. And I'm thinking about the consumption of alcohol as not just pure alcohol, it's usually with mixed drinks, so a lot of sugar, and also caffeine is involved. Did you do any research on how caffeine might affect any of that, or I just know nothing about science?
No, that's fine. That's a really good question. I haven't. I'm pretty sure that people have looked at that, though. I just am drawing a blank, because I know that there has been research on, for example, like those energy drinks like Red Bull and vodka and stuff like that, and how that differs from just drinking vodka.
Yes.
But, yeah, I mean, I don't know what that would have to do with OCT3, but I know that there is research like that out there. I just am not familiar with it as much, so. But yeah, good question.
Now, once again, we'll have a short break and go and please eat some food and stand up.
I actually have like first.
Twist my arms. Twist my arms.
Perfect amount of garden. You're so strong today.
Yesterday.
Oh, that's awesome. Because you didn't tell me earlier.
I was like, yeah, I couldn't find anything on the internet that looked quite right, so it was just like hand drawing step by step. It's awesome.
Okay, where do you race?
Huh?
Where do you race?
Yeah.
I hate it.
She said just kidding.
I didn't hear the.
I heard the just kidding.
Okay, good. I did.
I heard the just kidding.
When do you get tattoos then?
Yeah.
I have done that, but I'm not. Oh, yes.
I did it pretty well myself.
I think you have to try. You have to go find a way to come up and start right now. I have a cousin.
So, I don't know if it counts, but when I lived, in the boondocks of Wisconsin, there's tons of places where you can just real fast.
Yeah.
In open spaces, and I did that a lot. With only like one
My son's
square meter ass.
Okay.
Yeah.
I can do it. Those are essays. All of those are
Yeah.
essays.
Oh, yes, oh. Yeah.
There's a difference between being an actor. So is there a history to the one else? Is there a history to the one else?
You can ask my mom, I didn't know why I lived here.
Yeah.
She always told me that it's because they named me after Phil Collins.
That is true.
And only has one else.
Phil Collins
Does he?
does.
That's how you feel about.
Yeah, I can't see.
Phil Collins is a great person.
So do you play drums?
Depends on what you count as a drum.
You're talking to a drum.
I had a drum set as a kid, but I didn't stick to it.
Play saxophone.
A little bit. My older brother has all the music.
Congrats on your supercomputer funding.
Yeah.
Now we're going to have our third of the three presentations by Dr. Philip Krostowski. He's an assistant professor of physics whose research specializes in theoretical and computational quantum information science. Dr. Krostowski is joining Waldorf after a 3-year research position at Sandia National Laboratories, working in understanding the physics of state-of-the-art quantum sensing devices in service of the nation's national security mission. The research program he plans to build at Waldorf University, involving students, will tackle understanding the fundamental physics of quantum technologies and solving major issues slowing down the progress of true commercial quantum technologies and devices. Lastly, he plans to use his expertise to update the physics curriculum to benefit the entire student body.
Okay, so you may have seen this going around if you watch reels or something. There's this professor, he's a physics professor. He stands in front of the classroom for a quantum class and says, "Welcome, you don't understand anything, and by the end of it, you're just going to not understand it a little better than before." So that's what we're going to do today, because I don't really understand it either. But mainly what we're going to talk about is you're going to get another history lesson, because we need to talk about what quantum mechanics is before we can really talk about the research I've been doing. We'll talk about what I mean by quantum systems, and then the modeling I've done, and then the current and work I plan to do in other areas of interest I have. So what is quantum mechanics and where this whole revolution began? In circa 1900, the atomic revolution began because we were thinking about what happens when we just keep grinding things down. We have to get to something fundamentally small, and this gave us the atomic and subatomic level, where we have singular atoms, we have the electrons, the protons, and the neutrons. And these are the building blocks that make up everything around us, all the carbon atoms in our body, and so forth. The thing is when you start looking at the physics at a very small level, it starts to act strangely and not what we had thought was going on for a few hundred years since Newton really started physics. The big thing, and because physicists are very dramatic, we called it the ultraviolet catastrophe, because the physics at the time was not making sense if you consider an atom in what we call thermal equilibrium, its lowest energy state. So for us, tonight, our lowest energy state will be us in our beds going to sleep, because we're not moving. So our energy is at its lowest. Our current theory failed. So you see these three graphs. Our classical theory that followed Newtonian mechanics said that if you put enough temperature into something, the energy is just going to go off to infinity, which doesn't make sense. It shouldn't do that. It means it breaks down. Anytime you see infinities, we call them like singularities, something is wrong, because we can't have that happen. But our theory thought of it, if you take in physics 1, is you can put infinite amount of energy. It's just some continuous value that goes from 0 to infinity. Well, Max Planck came around and thought of, what if we introduced this thing called the quanta, meaning just we quantize energy into a single discrete value instead of a continuous value. It has to be one value or something else. It can't be anything in between. Well, in doing so, he saved all of physics, because on the left here is our actual spectral radiance of what we call a black body, something in thermal equilibrium that absorbs everything and gives off every kind of wavelength, depending on what temperature you give it. So physics is saved. We can go on and continue working on it. So this is what we call the old quantum mechanics, and you can see the X-ray of my head up there. But old quantum mechanics gave us these technologies. It gave us the cosmic microwave background, which tells us the entire history of the universe. It gave us X-ray technology, as well as nuclear power and nuclear energy. So we're going to jump 25 years and get to modern quantum mechanics. So you may not know this, but it is the 100-year anniversary of Schrodinger's wave equation. So because, again, physicists are dramatic, we named the year after this. For this year, we're celebrating quantum science and technology because of Schrodinger's equation and the anniversary of it. But what came from this is this duality, that a particle does not just act like a ball, but it also acts like a wave. And this is actually in its heart why you have X-ray technology and electron microscopes, because we treat these things no longer as a ball, but as waves themselves. But what we also learned is 2 years later, after there's a huge story that Werner Heisenberg went off to this island and was sick. And in his days of sickness, he thought of this uncertainty principle, that you can't know position perfectly basically, if you understand something's velocity, if you understand its velocity, you can't understand its position. Well, what does this tell us? I mean, right there, it doesn't tell us much. Like, what does that even mean? What it really means is that our world actually lives in probabilities, and Einstein absolutely, they say he absolutely hated it, but he worked with it for a very long time. So now things don't happen because they happen because probably they will happen, and then when we look at it, okay, our uncertainty in that has dropped and it's happened that way. So I am summarizing a lot of quantum mechanics here for you, but what I get interested in is something we call a particle spin. So it's fundamental to it, and you can think of it as a top, literally like a spinning top on a table. You can point upwards, but let's say we can also have it point downwards. And so this is it has to do with its internal angular momentum. We always thought of the atom as a central nuclei with an electron that was orbiting around it. Well, if it's orbiting around it, it has angular momentum because it's moving radially around it. This is part of it, but nothing's actually spinning. So I'm already going to tell you that we name it something that it's not doing. It's not spinning, but it's just something we call it because we don't know what it is. But the thing is we can actually work with it and use it to build amazing technologies that you're seeing all around in the news. And one thing is if we know this fundamental thing of spin, we know so much about it. We know its energy, we know its magnetic field, we know the atom's type, and it would go on and on. And this is the big thing that Feynman said why quantum computers are going to be so much better, is because in computers you have ones and zeros. It's two states. Well, if I give you a spin, I can give you 10 or 12 states, and you exponentially grow in information. So this started this whole spark into our new modern quantum mechanics. So we're still behind. We're still like talking about 100 years ago. So then what are these quantum systems? We're interested in this spin. We can control it. It gives us a lot of information. Well, one thing you might have seen, if you Google this, you will literally find Google's quantum computer they are working on. And what this does is it takes something spin and it gives it information like it would be a 1 or 0. If it's spin up, so the top is pointed up, it's a 1. If it's pointed down, it's a 0. And then they can build these computing devices that can do one thing right now, factor very large numbers. Isn't that fun? What is that useful to anyone? Nothing. It's not useful yet to me, so I'm sure I have colleagues that would say I'm wrong, but I don't really need to factor huge numbers, so I have no use for them. The other thing is this thing has to use these very large liquid cooling tanks to keep these things cool, because one thing with these spins is that when they interact with the environment around them. So if you are at any sort of temperature, you're interacting with heat, and because it's so sensitive, that very nice spin starts to move around or flip, and now we've lost everything we know about it, just because of this interaction. And just because I like to poke at quantum computing people, Microsoft announced their quantum chip earlier this year, and we're telling everybody in 5 years they're going to have thousands of these chips. If you look at their Nature paper, it clearly states by the editor that they have no evidence of the thing they're trying to say is the big thing about it. So, quantum computing is going to be 5 years away for the next 20. But the area I consider most prevalent and the area that's going to see the big technological revolution here relatively soon are in quantum sensors. So here, this is a quantum diamond sensor, and we'll talk more about that in a moment. But what we're looking at, and I want to focus mainly on this right image here. So on the left side, you have this normal microscope image we've all seen, and pretty sure we have some on campus, and all hospitals have them. They're looking at a sample of blood. Well, it's just a bunch of black and white, because they don't notice anything, it's just noise. On the right, one of these quantum diamond magnetometers, it's measuring the magnetic field from this same sample. You see this thing light up. And what that is a tumor cell. very small one. These can be on micrometers in size. So you can catch them very, very, very early, and these chips can be about that big or smaller. We just pump it with some light, because we control these spins, and then it senses that tumor cell, and it will pick it up. It's very accurate, and very useful. And the big thing about these is you can use these at room temperature. We don't need these cooling devices. They sit on a chip like any chip you find in your phone, and it can do these amazing things. Now, one of the big issues is at room temperature and in any place where you have it interact with this environment, there's a thing we call noise, meaning it's interacting with things we don't want it to. We can't bias these things out. So that's what a lot of my graduate research was on, and I published 3 papers on trying to figure out what all these noise effects are, what's the physics going on, and how can we train them out. And the latest one on that was with some experimentalists at Sandia, and the models are kind of pointing in the best way to start making these into real devices. And if those projects still have funds, maybe they're pushing it forward, but who knows. Another area are these things called atom interferometers, and they study very fundamental things. So on the left here is the MAGIS project at Fermilab, and the right is an image from our own lab at Sandia. What it is we're cooling down these atoms. Now I'm saying cooling, and you're like, oh, you brought those big old tanks back. But no, we're just using some laser beams to cool things down to the micro-Kelvin temperature. So all we do is we have these atoms and we put them in a vacuum chamber and we just slow them down, because all temperature is kinetic energy, meaning how fast you are moving. And what we can do is we can have it fall, and we can link Newtonian mechanics, which is not supposed to be here. This is quantum mechanics. It was hundreds of years ago. How do these two things link? Well, one of my colleagues literally says, due to magic, we can have these two things linking. And we can measure things down to 14 decimal places in accuracy. And because Newtonian mechanics has to do with things falling or things moving with mass, I have colleagues at Naval Postgraduate School that have this huge pendulum that they hang. It's been in their building forever. They want to use one of these to literally measure exactly how it's moving with perfect accuracy. And that's all I'll say on that, because that's all I can say on that. But now we'll get into where I'm interested. We're saying we have all these beautiful things we can do with these. We're talking about this very foreign thing called a spin. So what was my interest? So I looked at these quantum diamonds, and what they are really are little defects in these diamonds. So here on the left is diamond you're all familiar with. They're on your rings. It's just carbon that's set into a certain state, crystal structure. But nothing in reality is perfect, so it's not all carbon. You can have little defects happen. So in this one, you have a nitrogen atom come in, it knocks 2 carbon atoms out, and it leaves a vacancy. What that vacancy does is it leaves 3 electrons, 2 will bond together, and 1 will be free. And these electrons are the things that have spin. So if we pump this with a laser beam, we can control that spin to have it be pointed in one way or the other, and then use it as a sensing device. Another one is silicon carbide. Silicon is essentially the same thing as carbon. That's why there's all those sci-fi movies about silicon-based life, because it's essentially just carbon. It's just humans decided to be made out of carbon and not silicon. Who knows? So silicon carbide is just a similar crystal structure, but you have silicon atoms and carbon atoms. So you can have similar vacancies. So this is in a program that I use that's free in the University of Chicago in Champaign lets out. But the green atoms here are carbon, the yellow are silicon, and we have this free empty space. So what was interesting about this is one of my colleagues was working with some experimentalists at the Naval Research Lab, and they were noticing this temperature anomaly. So as I said, when we increase temperature, this thing called spin interacts, and we lose it. So how long we have that information we call coherence time. Coherent just means you have, everything is the same for a while. So as temperature increases, we should see it just decrease. They noticed this strange peak, that at some temperature, things started to turn around and our coherence started to increase because of it. It doesn't make any sense. And there were also similar observations done 10 years before that looked at this electron's resonance, just meaning it was giving off some light, and noticed it disappeared immediately. So for 10 years, we've had 3 sets of data that saw this and no idea what the hell was going on. So that's where we came in and started to look at what actually might be happening. So one thing that is starting to occur here, and again, I'm trying not to be too technical, but in crystals like everything likes to be at an equilibrium. You know, we talked about thermal equilibrium earlier. But when you have a defect, your crystal is not. So it wants to try and do that. So it will spontaneously distort itself to do so. And this is called the Jan-Teller effect from Edward Teller, and I forget Jan's name, so I'm sure he doesn't mind because I'm sure he's all dead. So what happens, though, is that this free electron in there starts to couple with the nuclei around it, meaning that whatever the nuclei is doing, it's trying to just be a part with it. And these couplings can get very strong. And we call it this quasi-particle because we can make this coupling, and we'll just treat it as a particle. Just like in the physics class, we always talk about how cows are just spheres. Or when I'm drawing free body diagrams of a truck, I draw a box and say, look how well I drew this truck. Because we can just assume something as this particle-like, even though it's really not. And we call this a polaron. And as this device starts to heat up, this electron starts hopping around from these nuclear sites. So this we'll say this polaron is moving around. And what happens is these fluctuations start to die down. So our theoretical approach here is we have this cause that's going on. This distortion happens, this electron starts coupling with everything nearby, and it just starts jumping around, having a good old time as things heat up. But the thing is it took a lot of work. It took us deriving models analytically, meaning with lots of equations, as I showed you 2 so far, so I'm not going to show you anymore. Because if you really want to read it, I can send it to you. You can read it and fall asleep halfway through. That's fine. And then also numerically, because some of these things don't have analytical solutions. So we need a supercomputer or a PhD student's laptop, which is what we were using, to model some of these parameters we need to then build our full model. And so we're just looking at this one effect. And what we notice here, so these dashed orange, the solid blue, and the dashed red line are models. And we're looking at either if you have a carbon vacancy, and it can have a positive or negative charge, or the silicon vacancy. And then I just re-implemented the actual experimental data onto this, and we see 2 effects. We see for the carbon atoms at about 20 Kelvin, so this is absolute temperature. 0 is as far as you can go. So 20 is still just very cold. Room temperature is about 273, depending on where you are. And we see this increase to this peak at about 120 Kelvin, and then it starts to decay. Well, this agrees very well with that data we've seen before. And if you look at this dashed line, it starts to go up at about 40 Kelvin, peaks at about 170 or so before it decays back, which is agreeing well and close with what they've seen experimentally, but not exactly. As you can see, they have this initial decay that doesn't show up here. And so far, we've only considered our one model. Experiments can't do that. They can't bias out everything that could be happening here. So we're very close with just our model so far. But let's just add one thing in. And so what we add here is something called a phonon reaction. Just the vibrations start these things to decohere. And at low temperatures, then that initial decrease appears. Our minimum point before we increase moves to 60 Kelvin, which agrees extremely well with their experimental data, and our peak moves back a little bit to 160 Kelvin, agreeing exactly with experimental data. So what does that tell us? It tells us that this one effect we've come up with, this theory, is agreeing almost perfectly with experimental data, and to this point, the only experimental data that has done anything like this. So our model must work. But that's great. You know, we can send it off to them, they can work at it. But the real big takeaway here is there is something universal going on here. So Newton's laws are universal because F always equals ma. There's a force, there's a net force, you will always have some acceleration. So that's why it's universal. No matter what you're talking about, you have that. So we had in mind this specific quantum system. But the model is built in general, meaning we didn't take into account our system when we were deriving anything. So what that means is if we have this polaron formation due to this distortion and this type of defect, it could happen in every type of material that does this. And this type of effect has also been seen in situations that aren't even like this. It's been seen in thin film semiconductors and so forth. But it can all be described by this one model. The other thing is that there is, a push to try and find more of these defects, because one thing, I don't know about you guys, but I don't like spending a lot of money all the time if I want to build one sensor, because diamonds are expensive. Even if you make them in a lab in Germany, which most people do, they get them shipped here. They do this whole process to get rid of non-idealities. But if we could find something that is cheaper to make, has this effect happen where this coherence, this thing we love, where we I know exactly what is happening in the spin, and it peaks at room temperature, we could find a device that could then just be it's cheap to make, we could have it everywhere, and we could put them in those little microscopes that could find tumor cells early on. So this is new, and we recently had this published online 2 weeks ago, I think the 29th of September, about 2 weeks ago. I feel it's a lot longer, because it's the middle of the semester. Well, no, actually it's near the end of the semester. No, it feels like the middle of it. So what am I doing now? I've already had this. I should hang up my socks or my towel? I don't know.
Or your socks.
Or my socks. Hang it up. I have my thing. They'll write books about me. They'll name something after me. We still have a lot to do, because one thing is a lot of those numerical things that we needed, the student's laptop or a computer to work with are very extensive calculations. So we did have to approximate a little for them. So we want to build a full temperature-dependent model. One, because as physicists, you can't just stop at an approximation. You assume that so that the students don't throw stuff at you and make it easier for them. But we really need to dive a bit further into that. We also do want to extend this out of silicon carbide into other types of materials, because it's our model. We can send it out to people, but then they have to learn and understand it. So why don't we just start doing that for them? And maybe we'll find one of these devices that do really well. And determining other noise sources, because the thing is what noise could be happening in an experiment is not easy. It changes based off experimental setup, and there's still a lot that people question about. And experimentalists are great; they have great intuition, but actually knowing what's going on is the only thing to really push them any further. But then I'm just going to switch gears on you guys. So how's that sound? Because I'm also using this to market myself. Essentially, my dissertation work was looking at some atomistic modeling of carbon's fundamental phase diagram, and I bring that up because it has been recently funded to build one of those computers here and fund some students, so we're going to push that along. Don't thank me, thank NASA for somehow having too much money. Because they sent out something that said they need to give more money away, so that's nice. But here's Vivian. I don't know why she's called Vivian, but my dissertation advisor calls her Vivian. It's a little pre-solar grain from a meteorite that hit in Australia. And they were studying it. It's pure carbon. When they looked at the center of this green circle in an electron microscope, they see these weird bends. So you all know graphite, right? It's in our pencils. Graphite likes to form sheets, very flat. Well, here, this graphite forms some sort of bend. And one thing is looking at something like this, we can start actually telling the history of where this came from. So, the theory at the time was that it came from some red giant star that supernovaed as it pushed the carbon out. And that carbon that was just a heated gas had actual graphene and graphite form around it, but the inside super cool. So it's still liquid in the middle before it solidified. And maybe that's why that would happen. But if you do that, this is the normal phase diagram, and it's very technical. But I'm going to tell you that based off this and what we think happened, it's completely wrong. My dissertation was looking at that and actually seeing where we need to change this phase diagram. But there's still a lot of work to be done on that. So why would you want to do on this? We're understanding carbon at its most fundamental level, and we can actually start telling the history of how carbon came to our planet and how we all started. Just based off understanding how carbon solidifies from a star that just gets ejected from some other galaxy. So we call it Vivian because we like to talk about Vivian's journey and her story. Because again, we're dramatic as physicists. We like to tell very dramatic stories. But the other thing is how these things actually form could create a new diffusion barrier. So we have all these tanks of gas, and we don't want them to escape. But most of anything is empty space. So after a while, things do diffuse out. It's actually how we get whiskey and wine. It diffuses into the barrel and it comes back. But you don't want that to your liquid nitrogen because it's expensive, and you don't want it leaving, and you don't because you have experiments you're trying to do. But my dissertation advisor, because he doesn't know how not to work, has been looking at this, and this diffusion barrier could be 2 times greater than the best one we have right now. At one point he said about 10 times greater, but he's brought himself back. But it would be understanding how to make this carbon solidify in a certain way in the lab. Because one thing about carbon in its liquid form, it requires pressures only found in stars and temperatures only found in stars. So if you know how to do that here on Earth, let me know so I can steal it and get the Nobel Prize. No, we'll share. But I talk too fast, so I'm already kind of done here. But I do want to thank DSU, where I did my master's, and my colleagues there. They're the ones that we worked on this temperature anomaly with. University of Missouri St. Louis is bringing in this funding through the Missouri Space Grant Consortium, Sandia, the Nuclear National Security Agency, and the Department of Defense, who also funded the research we just published. So now it's questions, which I know you needed the most time for, because everyone's mind is blown. And to show you I'm not lying, there's
AI.
If there's no question, it just means everyone's understood, so I can give you a test now and pass it. Yes.
Very basic. So
diamonds are produced in Germany.
Mhm.
Number one, how large are they? And number two, I assume the imperfections, the anomalies are simply spontaneous things that happen because the diamond creation process is not perfect.
Yeah, and you can choose to have them as big as you want. Normally, they'll come in like little discs, but like that looks like an actual CD or DVD, and then they can kind of divvy off and take what they want of it, so they get the most out of it. But yeah, and the
diamond
defects.
is flat.
Yeah, because they're literally forging it just in a lab. They're making these diamonds. So, they don't try and find natural ones. They're not sending miners into the mines.
There's one hell of a lot of pressure.
I don't think, I mean, some labs get tons of funding, but I still think it's a lot of paperwork to have people go out and get you diamonds.
Yeah.
We try not to work with other humans, not just because we're introverted.
Or are there particular imperfections that are selected for, or is there so many things, I mean, do they have to have a particular type of imperfection? Do they have to have a particular type of intervening atom or?
Yeah, so it has to be what we call a point defect. So you have a singular, the one thing with silicon carbide is it's interesting is you could have both of those atoms around an empty space in the middle be gone and it could still work just due to its crystal structure, but you're trying to get an isolated thing. And the thing is, this is one site, so you will get an ensemble of them, but it's more that this point defect. You can have other defects that are like the crystal structure shifting, and it kind of bends, but it's more that these point defects are what we call them color centers, because they actually do give the diamond different colors. Because we just like to be right.
I'm just curious, but who is really interested in is the appeal of like using this technology of the spin, which I keep thinking wrong with it, and because that's how I'm picturing it. Is that in the terms of computing, is it more useful because it allows for like more data storage, or is it more of a speed thing?
Both.
Both?
Because a spin gives you a 1 and a 0, depending on how it is, gives you a certain number value in a certain computer. It's binary notation. And based off what that number is, we take it and display all these cool graphics on our computers now. The thing is with the singular spin, but they call it the qubit because it can be like up or down. So that gives us our 2, our 1s and 0s. But it doesn't just give us 1 or 0. It also gives, the spin has a frequency it's spinning at. It has a certain amount of energy. So you get all of this information. And due to Heisenberg, all that information is actually linked together in some way. So once we know that, we know all of this. So you're just giving yourself an exponential amount of information, which then speeds up any computation.
For those of us who are visually imaginative learners,
Yes.
Would that be like the difference between a light switch that goes on and off and a dimmer? We could pick whatever we want.
Yeah.
You mentioned Department of Defense funding, and Dr. Falk, you mentioned national security. What are national security implications?
So my department works in nuclear non-proliferation, so kind of treaty verification. So that's where these and how we use them. We can shut the doors, turn the live stream off. If we can, a lot of these things are compact. They're literally small chips, but they can sense, they're very, very sensitive to their external surroundings, so we can shrink down our devices. And what I've learned is do some very interesting things I never even thought about. So.
The spikes happened at 60 degrees Kelvin and 160. Are there any other anomalies or things at that temperature that you notice in other
we've only looked at this, and that is currently the only experimental data that's done this systematic process. Because our knowledge was to increase the temperature, your coherence just goes down. So we're going to go off of that, because that's what we expect. So the experimentalists just our big thing is working at room temperature, so a lot of people just work there. But what if we shift a little bit, we can actually boost performance? We just don't know. And that's why, now that we have this and done this, we can kind of maybe open doors into looking at it a bit closer. Because, yeah, there's 3 references that bring this up in this type of quantum defect.
That were reproducible. They showed up.
Yeah, and they're doing 2 different types of experiments, but they're saying the same thing. So, and our model fits it very, very accurately, but it's not something that people have thought about. So hopefully it opens doors. That's why I'm going to go give this talk at a conference in March, so the people that I can start screaming at people's faces. It'll be more technical though, so. Sorry. No, if you want to, it's going to be in Denver.
I'll make a movie about it.
It'll be probably 15,000 physicists there. Yeah, it's the biggest conference of the year.
Cocaine and alcohol, or?
Is there a designated